Good afternoon. Just looking into what we have with the remaining set of test 3 review items, and we have for this bonus set, okay, and we have for the first problem, okay, we have a quadratic function that is presented in standard form, and we have for this item we have a function f of x equals negative 3x squared minus 12x plus 17, and if we look at taking what we have and converting ultimately into the vertex form. Okay, so we have for this function, we can start out again using parentheses, okay, to enclose the variable terms and separate them from the constant which we have with the 17 that is being added. And so for right now we have the quantity of negative 3x squared minus 12x followed by the addition of 17, and to be able to set the stage whereupon I can utilize the completion of the square as an intermediate process to getting to the vertex form. Okay, I want the first term in the parentheses, okay, to be x squared, and right now I have the leading coefficient at minus 3. And so if I look at factoring out negative 3 and placing outside the parentheses, so I'm going to have in the rewrite, we have negative 3 times the quantity of x squared. Next term, negative 3 into negative 12x is going to be a positive 4x. Again, we have followed by the addition of 17. And looking at what we have now, okay, so I have x squared plus 4x, first term in the parentheses is now x squared. And for setting up the completion of the square, I can take what is next to the first order variable x. In this case, we have the coefficient 4, and again, for the completion of the square, I'm going to take half that value and square out. So you have half of 4 is going to be 2. And 2 squared is equal to 4. And the number 2, which you just squared, that is ultimately going to reappear in the vertex form. And so looking at what we have after identifying 4 as a constant, that will be added inside the parentheses. So we now have f of x is equal to negative 3 times the quantity of x squared plus 4x. And then we have the addition of 4. And again, we have followed by the addition of 17. And okay, so I'm adding 4 within the parentheses. But for what I'm doing, in effect, is that as I'm adding 4 within the parentheses, I'm actually adding negative 3 times 4 at the front. And by adding 4, I'm collectively amounting to the subtraction of 12 from what I had earlier. So to offset this imbalance created, okay, so if I'm in effect adding negative 12 at the front, I'm going to offset by adding 12 at the back. So for what I'm going to have here, we have that f of x is equal to negative 3 times the quantity of x squared plus 4x plus 4 and then we have followed by 17 plus 12, which is going to be at 29. Okay, now you can always double check, okay, because here we have negative 3 over this trinomial. Again, we have negative 3x squared minus 12x. Negative 3 times 4 is negative 12, and if I add 29 to negative 12, I'm back to where I was with plus 17. Okay, but I'm looking at converting this squared trinomial in terms of the binomial that it is going to be the perfect square of. So we have for f of x, we have negative 3, once again, we have times the quantity. Now for x squared plus 4x plus 4, we have a squared trinomial. And again, for x squared, okay, that is the square of x. And again, how I formed this trinomial was made possible upon adding 4, which originated from the completion of the square stage where we had squared out positive 2. And so again, that 2 reappears. So we have negative 3 times the square of the binomial x plus 2, and we have followed by the addition of 29. So this is going to be the resulting vertex form. And in terms of the items addressed in this first problem, okay, so we got the vertex form. Okay, and so we have, in reference to the coefficient a is equal to negative 3, and because we have a negative for the leading coefficient, okay, that means that in this particular case, all right, you're going to have the graph opens down from the vertex, and since the graph is opening down from the vertex, that means that the vertex is going to be the high point, and the vertex will be regarded as the maximum. And for what we have regarding the h and the k values, okay, so we have with x plus 2, okay, so remember x plus 2 is in representation of x minus h. So you have x minus h equal to 0, and that is represented in this application by the binomial x plus 2. And if x plus 2 is equal to 0, so we have that x is equal to negative 2. Okay, so our x coordinate, or our h value, is going to be at minus 2. And for the number 29 that follows, okay, so we will have that, essentially have that k is the y coordinates, okay, and in this case we have at 29. Okay, so in the case of the vertex, okay, so in the Cartesian coordinate system, or xy coordinate system, okay, you have x paired up with y, and from the vertex equation, okay, we have h and k, so we have negative 2 and 29. And so in terms of addressing what we have here, okay, so it's asking, does the function have a minimum or maximum value? Okay, and since the vertex is a high point, okay, this one is going to have a maximum. And then we have for the next part, okay, is asking where does the minimum or maximum value occur? And that is going to be what we have for the h, or the x value. So it's going to occur at negative 2. Okay, we can say that x is equal to h is equal to negative 2. And in terms of what is going to be the minimum or the maximum value, okay, and the maximum value is going to be the corresponding y value. And so in this case, we're going to have that y is equal to k is equal to 29. Okay, so again, we have maximum since the vertex is the high point, okay, because the graph is opening downward as indicated by the negative leading coefficient. And again, the maximum value occurs at the vertex at x is equal to h is equal to negative 2, and we will have the high value being the y or k value, which we have at 29. And just looking at what we have as a visual, okay, so we got with this item here, okay, so we got with the graph of this particular quadratic function, okay, so we got, again, so you have the graph of y is equal to f of x is equal to negative 3x squared minus 12x plus 17. And again, you have your vertex at negative 229, and again the graph opens down from that location. All right, now for what we have in the case of the next item, and we have we're looking at in behavior, and for starters, okay, and we have given function, okay, that is in factored form, and we have in this particular layout, okay, so we got that f of x is equal to 3x squared, and we have times the quantity of x plus 5, and we have times the quantity, okay, we have of 3 minus 2x, which is raised to the third, okay. And now, concerning the end behavior of the graph of this function, okay. And so just looking at what we have now, okay, so we got this function, and now to determine the end behavior, okay, I need to be able to identify what, if I were to multiply these expressions out, what the highest degree term will be. Okay, so we have for the highest degree term, okay, so just looking at the components, okay, so you have at the front, we got 3 in front, okay, as a coefficient of the first factor, okay, so just taking the main components here, so we have at the front, okay, so we got 3x squared, and we have, in the case of x plus 5, okay, we say we have x plus 5 to the first, okay, so between x and 5, okay, we'll have x to the first, and for 3 minus 2x, now between 3 and negative 2x, now negative 2x is going to be the higher order term in x, and from the cube of this expression, we take that term and raise to the third. So we have from the front, again we have 3x squared, so we got 3x squared from the front. The next, okay, we have like x to the first, and from 3 minus 2x, take the higher order term in the variable factor. So we got negative 2x, which is to the third. And for what we have in following through, okay, okay, so I have 3x squared times x, and for the cube of negative 2x, they go like negative 2 times itself will be at negative 8, and with x to the third, we have x cubed. Okay, so we're looking at 3x squared times x times negative 8x cubed, and so we have in the product, we've got 3 times negative 8 is negative 24, and in x, we have x squared times x is x cubed, and x cubed times x cubed is x to the 6th. And so we have with our highest degree term, we have the leading coefficient to be at minus 24, okay, which is going to be negative. And for what we have in terms of the degree of the function, okay, this comes from the 6th order of x. So we have that n is equal to 6. Which is an even value. And so this is going to signal that for what we have concerning the end behavior, okay, so you have an even powered function, so both to the left and to the right, it's either going to move up on both sides or move down both sides. And with the leading coefficient negative, you have a negative coefficient, even power, and so in this case we'll have motion down to the left and down to the right, or falls to the left, falls to the right. Right. So this is what we have in the first part. Okay, and now for what we have in the case of the next portion, and this is going to be concerning what we have with the zeros and their multiplicities, and also where the graph crosses and touches the x-axis. Okay, so for what we have in the case of the rational function, or I should say the polynomial function, okay, so you have three distinct factors in x. You have x, which is to the second, you have x plus 5, and you have 3 minus 2x, which is to the third. And so if I stress the degrees once again, and in the case of what we have for the zeros of the function, okay, so we have just from the x factor, nothing is added or taken away from x, and if that's the case, well, the corresponding x factor is going to have a 0 value. And for x plus 5, we have, if I set that equal to 0, we have that x is equal to negative 5. Okay, now for 3 minus 2x, okay, a little different arrangement. And if I were to have set this equal to 0, we have like negative 2x is equal to negative 3, and so you have that x is equal to 3 halves, and you can also write that as a decimal at 1.5. And for what we have concerning the multiplicity, okay, so you have 0 stems from, again, the first x factor, where we had the variable to be raised to the second power. So 0 has a multiplicity of 2. X minus 5 stems from x plus 5, which implicitly is to the first degree. And 1.5, or 3 halves, okay, stems from 3 minus 2x, which is cubed. Okay, and so that multiplicity is going to be at 3. And in terms of whether the graph crosses or touches the x-axis, okay, so 0 has an even value multiplicity with 2, and zeros of even multiplicity will be locations where the graph is going to touch. So it's going to touch at x is equal to 0. And we have with negative 5, okay, negative 5 has a multiplicity of 1, and with 1 as an odd number, it's going to be at x equal to negative 5 that the graph is going to cross. So we have a cross at x is equal to negative 5, and then we have with the remaining 0, okay, we have at 1.5, okay, we have the multiplicity at 3, and 3 like 1 is an odd number, so the 0 value of 1.5 or 3 halves, okay, the graph is also going to cross. Okay, so crossing at x is equal to 3 halves, or again at 1.5. Okay, and now for what we have in the next item, and that is for part C, we're looking at determining, I believe, what the y-intercept is going to be, and then after that look at the general layout of what we have for the graph of this polynomial function. Okay, so for what we have in the case part C, for the y-intercept, okay, so you got this polynomial function, and let's say this is already going to be the origin. Okay, so you got 3 times 0 squared. 0 plus 5 is 5. And then we have 3 minus 0 is going to be 3 cubed. And guess what? Square root of 0 is 0, and that's going to create a domino effect. Okay, where we're going to have the y-intercept is going to be y is equal to 0. And if we write as an ordered pair, let's say we have, again, you have y is equal to 0, or as an ordered pair, you have the origin. And so looking at what we have now in the overall picture, okay, so you got your end behavior down to the left, down to the right. And again, we have 3 zeros, one where we have the graph of the function to touch the x-axis, okay, namely the origin, and the other 2 zeros we have the graph to cross, and we have, again, the y-intercept will be at the origin. And for what we have in the case of the graph, and just to get, I think I have the visual on this one. Yes, I do. Okay, so we got for this one. Okay, so you got your y-intercept at the origin and the end behavior. Okay, you have down to the left, down to the right, or falls to the left, falls to the right, and we have with our respective zeros. Okay, on the x-axis we have x equal to 0, x equal to -5, x equal to 3/2 or 1.5, and again the end behavior. Okay, you have extending from the leftmost and rightmost 0, so you have moving down both ways. And again, for the zeros on the x-axis at -5, okay, the graph crosses from below to above the x-axis, and then it's going to descend. And once we get to the origin, the graph is going to touch, essentially bounce off the x-axis to where it is back above the x-axis. Then once we look at the graph descending, and once we get past x is equal to 1.5 or x is equal to 3/2, you have the rest of the motion of the graph of this function f of x to be moving downward. Okay. Now, for what we have in the case of the next item, and we have in the third situation, now we're looking at the determination of the quotient and remainder of this particular rational function. And okay, so we got 2x plus 4 as the divisor, and for what we have in the case of the dividend, okay, we have 4x to the 4th plus 2x squared plus 6x. And in the setup for what we have for number 3, let's see if I can fit that in and move. Okay, so we got number 3. Okay, so we got 2x plus 4. I think I could. 4x to the 4, 2x squared, 6x. Okay. Okay, so in the case of polynomial division, okay, now I don't have the divisor such that I can directly use the synthetic division. And the reason being now is that while we have the variable x to be first degree, is that we have a coefficient other than 1 that is in front of x with the number 2, so you have a little bit of static that is created. And now we have with the dividend, again, that was 4x to the 4th plus 2x squared, and we have plus 6x. Okay, And again, for the dividend, we want all the degrees from the highest down to the constant to be represented. Okay, so we got 4x to the fourth. So we got a fourth order x term, but notice the next term is second degree. So the third order is missing. Okay, so I'm going to use 0x cubed, okay, as a 0 placeholder. And then we have 2x squared, and then we have plus 6x. And I want to close out the dividend with a constant. Okay, so I'm going to use yet another 0 for placeholder purposes. And so for what we have initiating the long division, okay, so we got the leading term from the divisor, 2x, into the leading term of the dividend, 4x to the fourth, and 2x into 4x to the fourth. 2 into 4 is 2, x into x to the fourth is going to be x cubed. And looking at distributing 2x cubed over the divisor, so we're going to have 4x to the fourth and 2x cubed over 4, so that is going to be 8x cubed okay. So for what we have in the first round of the long division, okay, again, the initial object is going to be to get the first term of the dividend out. Okay, so through the process, with the row by row subtracting, we'll have 4x to the fourth to go out, and now we have 0 minus 8x cubed, so we have a negative 8x cubed we have plus 2x squared, and we have plus 6x plus 0. So for the next phase, I can take 2x into negative 8x cubed. So that is going to be negative 4x squared times, and distributing, so we have negative 8x cubed, negative 4x squared times 4 is going to be a negative 16x squared. Now looking at subtracting, okay, so we got minus 8x cubed plus 8x cubed, that will go out. And we have 2x squared plus 16x squared, so this will be 18x squared. Yeah, plus 6x. And I can resume, okay, so you got 2x into 18x squared, so this will be 9x. And we have, upon distributing, once more, okay, so you have 18x squared. And 9x over 4 is going to be 36x. Again, we have subtract, so 18x squared will go out. And we've got 6x minus 36x. That'll be a negative 30x. Then we have one more term in the quotient, and that'll be 2x into negative 30x, so this will be negative 15, and distributing negative 15 over the divisor, so we have negative 30x minus 60, and subtract, okay, so negative 30 and positive 30x will go out. Then we've got 0 minus negative 60, and that's going to revert to adding 60. And I cannot take 2x directly into 60, since 60 is of a lower degree in x, since it doesn't even have the letter x in the first place. All right, so for the quotient and the remainder, okay, so the quotient will be how many times the divisor goes into the dividend. Okay, so you got the quotient again, so that's going to be 2x cubed minus 4x squared plus 9x minus 15. And for what we have in the case of the remainder, that's going to be that last row bit. Okay, so the remainder is going to be at 60. Right. So the quotient, you have a cubic polynomial with this set of terms, and again for the remainder, that will be 60. All right. Now, for what we have in the case of item number 4, okay, so we're looking at still working with quotient and remainder, and in this particular problem, we now got it where we have using synthetic division, okay, to find the quotient and remainder. Okay, here we have 2x cubed plus 2x minus 9 is divided by x minus 5. Okay, all right, so you got 2x cubed plus 2x minus 9 is all over x minus 5, okay, and we're looking at utilizing, again, synthetic division to discover the quotient and remainder, and then also we want to write the expression in terms of the quotient plus the ratio where we have the remainder over the divisor. Okay, so for what we have in this item, okay, so you've got 2x cubed plus 2x minus 9 all over x minus 5. And now if I set things up in terms of line division, again, the reason I'm doing this is just make sure I'm not missing any degree terms. So we have the divisor at x minus 5, and for the dividend, okay, so I have 2x cubed, and if you notice, we have a missing x squared term, and then we have plus 2x, a first degree. We have ending with the constant negative 9. And if I take what I have and translate in terms of synthetic division, all right, so to represent x minus 5, I'm going to take the 0 of this. Okay. And so for what I have in utilizing synthetic division, okay, I'm going to have the layout just a little bit different. I personally like the little elbow formation, but just kind of have it in line with how Alex puts things on display. All right, so I had the 0 value at 5, and for the coefficients of the dividend, okay, so I have 2 for the x cubed, 0 for the missing x squared. We've got 2 for the first order in x, and you'll have negative 9 for the constant. Okay. So looking at what we have with synthetic division, okay, so you're looking at column by column addition as opposed to row by row subtraction. Okay, so we've got 5 as the 0, and the first coefficient in the dividend is going to be the first coefficient in the quotient. So I'm going to bring down 2, and then we have 5 times 2 is 10, and the part will be brought over to the next column and adding. So we have 0 plus 10 is 10, and we have 5 times 10 is 50, and we've got 2 plus 50 is 52, and 5 times 52 is 260, and negative 9 plus 260, okay, that is going to be a 251. Okay, so we have, in the case of the last column total, okay, so you're going to have the remainder will be 251. As for what we have in terms of the quotients, okay, the terms will have the coefficients of 2, 10, and 52. Now again, the dividend has 2x cubed, but after each round of synthetic division, you have the degree originating from the dividend to go down 1 degree at a time. So this 2 at the front, this is going to reference 2x squared, and we have immediately next in line, we have plus 10x, and then we have 52. And just looking at what we have expressing this ratio in terms of quotient and remainder over divisor. Context. Okay, so you got 2x cubed plus 2x minus 9 over x minus 5 is going to be equal to 2x squared plus 10x plus 52, and you have plus 251 all over x minus 5. Right. Now, for what we have in the next case, okay, so we have with number 5. So we're looking at remainder and factor theorems. And for number 5, okay, it says to use the remainder theorem to find the quotient and remainder of p of 2. And right now, okay, we got the dividend, okay, p of x, okay, and see that for that expression, okay, so we got p of x is equal to, so you have 5x cubed minus 4x plus 7 and we're looking for p of 2, and you can find the quotient and remainder, okay, in different ways. And for what we have in the case of this particular problem, okay, so we're looking for p of 2. Okay, so just kind of setting things up for what we have here. Okay, if I apply synthetic division, okay, first of all, okay, we have p of 2. Okay, so 2 is going to be the 0. And to make sure I don't have any missing degree terms, okay, now p of x is going to be the dividend. And right now we got 5x cubed minus 4x plus 7. But again, okay, I'm missing a degree term. In this case, I'm missing a second order expression. Okay, and so we have in the rewrite, okay, we have 5x cubed plus 0x squared minus 4x plus 7. And if I utilize synthetic division, okay, so we got 2 as the 0 of the divisor, okay, and then we got 5 in reference to x cubed, 0 for the missing second degree term, and we have negative 4 for the first order x term in the dividend, and finally we have the number 7. And looking at what we have in the case of the synthetic division setup, okay, again, so we're looking at, again, column by column addition. Okay, so for what we have in the first case, all right, so 5 again is both the leading coefficient in the dividend and also in the quotient. So 5 is brought down. Now we got 2 times 5 is 10. This will be brought over to the next column. And we got 0 plus 10 is 10. Then we have 2 times 10 is 20. And negative 4 plus 20. Okay, so that is going to be at 16. And 2 times 16 is 32. And 7 plus 32 is going to end up at 39. Okay, so for what we have in effect, okay, is that, again, we have with the last column total, okay, that is going to be the remainder. And for what we have in terms of the quotient, okay, so we're transitioning from 5x cubed to 5x squared. So with the quotient, so we end up at 5x squared plus 10x plus 16. Let me make sure I got all of that. So for number 5, I believe it was asking for just the quotient and the remainder. Yep, it says to find the quotient and the remainder. Okay, and so we have in effect for the remainder of P of 2 let me just restate this. So P of 2, again, and the remainder will be one and the same. So P of 2 is equal to 39. All right. Now, in the case of what I have for number 6, okay, this is with the factor theorem, I believe, yes. Okay, and it says to use the factor theorem to determine if x plus 2 is a factor of P of x is equal to this 4-term trinomial of third degree. And we're looking at okay, just filling in the blanks, like P of the 0 of the divisor is equal to what remainder? And we had the yes or no question, is x plus 2 a factor of P of x? Okay, and so just taking what we have here, just going to write this down. So you got verse 6, so we have P of x. Again, we have is equal to x cubed minus 2x squared minus 3x plus 10. Okay, and I'll show you a couple of ways of going about this. Okay, so we got the divisor at x plus 2. So you got this polynomial. Okay. And one way that you can go about this, okay, is that taking what we have with the original polynomial. Okay. Now for the divisor, okay, we have x plus 2, and the remainder of using this divisor, okay, it's going to be taking the 0 of the divisor as the input for the dividend. So in other words, if I have like x plus 2 is equal to 0, I have x is equal to negative 2. And just kind of carrying over. So we have for the remainder, okay, that is going to be P of negative 2 okay, so for x to the third, so we're looking at the negative 2 to the third power minus 2 times the square of negative 2. And we have minus 3 times negative 2. followed by the addition of 10. So we got the cube of negative 2. Okay, so that's going to be negative 8. We got minus 2. Now the square of negative 2 is 4. Negative 3 times negative 2 is positive 6. We got plus 10. And right now we got negative 8. Negative 2 times 4 is negative 8. And I can go ahead and add 6 and 10 together. I'll just keep everything itemized. Okay, so for what we have now with these numbers, got negative 8 minus 8 is negative 16. Negative 16 plus 6 is negative 10. Negative 10 plus 10 is equal to 0. And since the remainder is equal to 0, since p of negative 2 is equal to 0, it's going to follow that x plus 2 is a factor. Okay. And that is one line of reasoning, okay, if you use the function value as the remainder. But again, if you had in mind the use of synthetic division, I'm going to show you this other approach. Okay, if you had in mind the use of synthetic division, okay, this is also going to work. Okay, so I have x plus 2. Again, we have into x cubed minus 2x squared minus 3x plus 10. Okay, if I translate what I have in the line division setup along the lines of synthetic division. Okay, so I got negative 2. Again, with the coefficients of the dividends, so we'll have 1, negative 2, negative 3, and positive 10. Okay, so again, so 1 is the leading coefficient from the dividend. This will be brought down. Then we have negative 2 times 1 is negative 2. Negative 2 plus negative 2 is negative 4. Negative 2 times negative 4 is 8. Negative 3 plus 8 is 5. Negative 2 times 5 is negative 10. And 10 plus negative 10 is 0. Okay. All right. So again, we have, in effect, that the remainder is equal to, again, p of negative 2, which is, again, going to be 0. Okay, so just relaying this back to what we have in number 6. Okay, so just for the numbers here, see if I can zoom in a little further. Okay, so for the result here, okay, so we have p of negative 2 is equal to 0, and is x plus 2 a factor of p of x? Well, since we had the remainder to be 0, the answer to that question is yes. Okay. All right. Now, for what we have in the case of inequalities, okay, and we have with this polynomial expression, okay, so we have that x squared minus 4x, okay, is less than or equal to 12. And so it's just to solve for the inequality. then what I'll do here, just add a page here. Okay, so we got x squared minus 4x is less than or equal to 12. And if I rewrite this in terms of comparing to 0, so we have x squared minus 4x minus 12 is less than or equal to 0. And so taking what we have here, okay, so rewriting as a comparison to 0 item, okay, so we'll just have f of x to be that trinomial compared to 0. And again, to be able to set up a table of intervals. Okay, so again, we'll say that we have f of x to be in reference to x squared minus 4x minus 12. And if I attain the zeros from this, okay, so we have x squared minus 4x minus 12 is equal to 0. And if I look at factoring, okay, so again we have with x plus 2 and x minus 6. If I set each of these factors to 0, okay, so we have x is equal to negative 2 and x equal to 6. Okay, so just in terms of what we have in the setup. Okay. Okay, so you have f of x equal to x squared minus 4x minus 12, and again the zeros of this function again we have at negative 2 and 6. Alright, and looking at setting up a table of intervals, I'll tell you what, let me let's go ahead and copy this table. Okay, so for what we're going to have in the setup, it's going to even up the spread here. Okay, so I'm going to set up a table of intervals involving this front function and centered about negative 2 and 6, the zeros. Okay, so we have for the first interval between negative 2 and 6. Okay, negative 2 is the smaller of the zeros. So for the first set of values of x in the table, we have those values of x less than negative 2. Then we have next in line, we have those values of x to test out where we have negative 2 is less than x is less than 6. And we have for the rest, we're going to have those values of x greater than 6. And for what we have in the case of the tested value, that we can select, okay, for the first, we can have anything that is less than negative 2. So we can go with, say, negative 3 is a choice. Between negative 2 and 6, I've always liked 0, and I'm going to go with this again. And anything greater than 6, okay, you just go with the number 7. And we have for our function, again, we have f of x is equal to x squared minus 4x minus 12. Okay, so we're looking at f of negative 3, f of 0, and f of 7. So plugging in negative 3. Okay, what's going to happen here? Got negative 3 squared is positive 9. Negative 4 times negative 3 is a positive 12. So we're going to have 9 plus 12 is going to be 21. Then turn around and take away 12. Take away just what I added. And so we're back to positive 9. And we have for f of 0. Okay, so we got 0 minus 12. So f of 0 is equal to negative 12. And then for 7 squared is 49. Negative 4 times 7 is negative 28. So you got 49 minus 28 is going to be 21. Take away 12. So you have f of 7 is equal to positive 9. And looking at the sign value of r of x, in this case f of x. Okay, so for values of x selected that are less than negative 2, like negative 3 being such a case, the output is going to be positive. So f of x is greater than 0. Then for what we have in the middle interval section, we're going to have a negative output. In the last case, we're back to where we're going to have a positive output. And now looking at what we have present. Okay, so this is the inequality we started out with. Is that x squared minus 4x is less than or equal to 12, and then translating in terms of comparing to 0. Is that x squared minus 4x minus 12 is less than or equal to 0, and that is in line with where we have f of x is less than or equal to 0. Okay. And so for what we're going to have in terms of the solution, okay, now less than or equal to 0 will be in the same direction as less than 0. And we're going to use the same numbers, okay, as the values to work around. So we're looking at negative 2 and 6. With the equal sign, there is the possibility of brackets in the mix. And since both negative 2 and 6 create the situation where the function is equal to 0, again, both of them, okay, negative 2 and 6 will both create the equal to 0 part. And so both the values will be in brackets. So your interval solution is all values of x such that negative 2 is less than or equal to x is less than or equal to 6. And so you have closed interval with brackets on both ends. All right. Now, for what we have in the case of number 8, and on this one case, you have x squared minus 4x over x plus 5, okay, is greater than or equal to 0. Okay. X squared minus 4, yep, over x plus 5 is greater than or equal to 0. Okay, so we've got, for this particular inequality, this is already in comparison to 0 terms. So we have r of x is greater than or equal to 0. And for what we have in the case of r of x, okay, so I have x squared minus 4x over x plus 5. Now we're just going to go ahead and write this out in factored form. Okay, so the numerator, greatest common factor is at x. Times the quantity of x minus 4. We have all over x plus 5. And for what we have in the case of the zeros of r of x, okay, and from the numerator, I can have a 0 numerator as long as I do not have a 0 denominator. So we got from x, we have x is equal to 0, and that value is in the domain from x minus 4 in the numerator. The 0 is going to be 4, and this is in the domain, but we have on the other hand for x plus 5, okay, if that is 0, then we have x at negative 5, but if I have x at negative 5 and we have a 0 value denominator, and that would create, instead of a 0 value for r of x, it would end up being an undefined expression. So negative 5 is not in the domain. And working with what we have among the zeros and setting up a table. Thought I had it. Okay, so just setting things up here. Okay, so we've got 3 distinct zeros. And for what we have in the mix, okay, out of negative 5, 4, and 0, okay, negative 5 is going to be the smallest of the 0 values. Okay, so we have at the lower ends, we're looking at those values of x. That'll be less than negative 5. And we have next in line, okay, so you have between negative 5 and 0. Then we have followed by, okay, in terms of what comes past 0, those values of x between but not including 0 and 4. And then finally we have those values of x which will be greater than 4. And for test values that we can supply. Okay, so anything that is less than negative 5, you can say we can go with negative 6. Between negative 5 and 0, as much as I would like to use 0, I cannot in this case. So I'll go with another integer. I'll just go with negative 1. Same thing here. I cannot use 0. So if I select an integer that is less than 4 and greater than 0, I'll just go with 1. And anything greater than 4, I'll just go with the number 5. And for what we have in the case of r of x, again, we have x squared minus 4x all over x plus 5. And looking at the outputs corresponding to the inputs of negative 6, negative 1, as well as 1 and 5. Okay, so for what we have in the case of negative 6, okay, kind of looking at this, we got negative 6 plus 5 is negative 1 in the denominator. And we got negative 6 squared is a positive 36. Negative 4 times negative 6 is going to be a positive 24. 36 plus 24 is 60. And divided by negative 1. So r of negative 6 is minus 60. For r of negative 1, okay, it's got the square of negative 1 is positive. And you got minus 4 times negative 1 also positive. So we have 1 plus 4 is 5. And then we have over negative 1 plus 5, which is 4. So r of negative 1, that is going to be a positive 5/4. And for r of 1, okay, so we have 1 minus 4 is negative 3. 1 plus 5 is 6. Negative 3/6 reduces to a negative 1/2. And for r of 5, okay, so you got 5 plus 5 is 10. And you got 5 squared is 25 minus 20 is 5. 5/10 is going to be a positive 1/2. And for what we have in the case of the sign value of r of x in the first interval, okay, this is going to be negative. In the second, okay, this is going to be positive. In the third, okay, we have a negative. In the last, we're going to have a positive. And just reverting, okay, to the original inequality. Okay, so already this is a comparison to zero inequality, and we're looking at, in essence, what is going to be where the function is greater than or equal to 0, and for what we will have in terms of the solution. Okay, so we have in the same direction as greater than 0, so we're involving the limit values negative 5 and 0, as well as 4 and infinity. And okay, so in terms of the enclosure, okay, now at all values infinity, positive and negative, we'll maintain the use of parentheses. Now with the equal sign, there is the possible insertion of brackets. Not a guarantee though. Now we have for looking at negative 5, okay, again, negative 5 again would create a 0 value denominator, so that is not in the domain, so that's going to stay in the parentheses. Now both 0 and 4 are in the domain, so those numbers will be enclosed in the brackets. Okay, and so this will be the interval solution for what we have for this particular rational inequality. And now for what we have in the case of number 9, so you have x plus 2 over x minus 6 is greater than or equal to 0. So you have another comparison to 0, rational inequality. And so we can say we have also the r of x is greater than or equal to 0. All right. So we have r of x is equal to x plus 2 all over x minus 6 And for the zeros of r of x, okay, we have again, we have with x plus 2, okay, we have negative 2. And you can have a 0 numerator again, as long as you don't have a 0 denominator. Okay, and negative 2, that will be the case. And for x minus 6, the denominator, if I have a 0 denominator, this will spring forth from x equal to 6. Again, any value in x that creates a 0 denominator is not going to be in the domain, and thus will not create the equal to 0 part for that particular rational function. And so we got two distinct zeros, and if we establish intervals around them, let me copy this yet again. Okay, so for what we have concerning the intervals, okay, so we have in the first lineup, okay, between negative 2 and 6, okay, negative 2 is going to be the smaller of the zeros. Okay, so we have at the lower end, so we have those values of x less than negative 2. And then you're going to have those values of x, okay, whereupon we have negative 2 is less than x is less than 6. And now for the rest, okay, we have those values of x which will be greater than 6. And entering the stage, okay, of applying the test values for the input. Okay, so we can say anything less than negative 2, we can go with minus 3. And we have anything between negative 2 and 6, we can go with 0. So we can use 0 this time around. Anything greater than 6, we'll just go with 7. So for what we have in the case of r of negative 3 and r of 0 and r of 7, okay, so we have with negative 3, have negative 3 plus 2 is negative 1, negative 3 minus 6 is negative 9, so we got negative 1 over negative 9, and a negative over a negative is a positive, so we have plus 1/9. For 0, we got 2 over negative 6, and 2 over negative 6 is reducible to negative 1/3. And in the case of 7, 7 plus 2 is 9, 7 minus 6 is 1, so you have a 9-to-1 ratio. So that's going to be plus 9. And for the sign of r of x, and we have here, so for the sign of r of x, okay, so I have a positive. So the r of x is greater than 0. Next we have the r of x is less than 0. Then we have last, okay, we have the r of x is greater than 0. And looking at the correspondence of what we have to arise with respect, okay, to what we have in the inequality we're trying to solve for. Okay, so again we have x plus 2 over x minus 6 is greater than or equal to 0. And again, this is going to be referencing whereupon we have r of x is greater than or equal to 0. And we have in the case of the solution. Okay, so you have in the same direction as where r of x is greater than 0. So again, we're involving negative infinity and negative 2, as well as 6 and infinity. And for the enclosures, now again, we have to remain open at the infinities, so you have parentheses to enclose. Now for negative 2, okay, negative 2 is in the domain, so that creates an equal to 0 part, so that is going to be in the bracket. And again, 6 is not in the denominator because we have the creation of a 0 denominator, which renders the rational expression as a value that is undefined. So that will be the interval solution for what we have in this case. And then for what we have in the case of the remaining inequality, and what I'm going to do here, we have in number 10, okay, so we got a comparison between ratios. Whereupon we have x over x plus 6 is greater than or equal to 1 over x. And if I convert, okay, to a comparison to 0 inequality, and what I'm going to do here, I'm just going to go ahead and consolidate this and just kind of leave a factored form in the mix. I'm just kind of skipping some steps here. So this is going to be the quantity of x plus 2 times that of x minus 3 all over x times, okay, the quantity of x plus 6 is greater than or equal to 0. Okay, so this is what we're going to have for r of x. We say r of x is greater than or equal to 0. So we say that we have for r of x okay, just putting this in terms of the factored form. Now for the zeros of r of x, okay, so from the numerator, okay, we got negative 2, and that's going to be in the domain, so I can have a 0 top part of the fraction. From x minus 3, we'll have 3, that is in the domain, and from the denominator, okay, so we'll have 0, that is not in the domain, and the 0 of the other denominator factor, that's going to be at negative 6. Okay, so we have 4 zeros, 2 that are in the domain and 2 that are not. And so just creating the spread. Okay, so for the intervals, okay, so negative 6 is going to be the smallest of the zeros. So the first interval, we have those values less than negative 6. Then we have between negative 6 and negative 2. And then we have between negative 2 and 0. And then we'll have between 0 and 3. And the 3 is the highest of the zeros. We have the remaining interval to be those values, x greater than 3. Okay, and for the test value x that we can apply for each of the respective intervals. So in the first, let's say -7. For the next, I'll just go with -3. And between -2 and 0, if I go with integers, I'm limited to -1. For the next, I can choose either 1 or 2. I'll just go with 1 in this case. And anything greater than 3, I'll just go with the number 4. And now, so we have with r of x, okay. Alright, so you have 5 distinct test values for the input. Now, for -7, okay, I've got this number available. Okay, so this is going to be at 57ths, which is positive. For r of -3, okay, so that's going to come out to -2/3. We have for r of -1, okay, that's going to be a positive 4/5. And for r of 1, okay, we have a minus 6/7. And for r of 4, okay, that's going to come out, once you reduce to lowest terms, that's going to end up at positive 3/20. Okay, and so we've got a positive, negative, positive, negative, positive. So you got the respective signs of r of x. So you have alternating between greater than and less than 0. And using the table as the reference. Okay, so this is the inequality we started with. And leading up to, okay, as a consolidated rational expression in comparison to 0. Okay, so you have r of x after the conversion of the inequality to one where we have in comparison to 0. All right, so you have in line with r of x is greater than or equal to 0. So you have in the same direction. That's where r of x is greater than 0. So now we are involving the limit values. Okay, so you have negative infinity and -6. And -2 and 0. as well as 3 and infinity. And for the enclosures, again, you have parentheses around negative and positive infinity. And for the rest, okay, you're going to have brackets around only the zeros in the domain. And first of all, we have -6, that is not in the domain. So we got our parentheses. -2, that is in the domain. So we have a bracket, 0, not in the domain. So that's in the parentheses. And finally we have 3, that is in the domain. And so that is going to be bracketed. Okay, so again, we have brackets around only those values that will create the equal to 0 parts. And everything else is either going to be boundless or be a finite value that causes the rational expression to become undefined.